For this question, we've got a particle P that's moving on the x-axis. At time t seconds, the displacement x meters from O is given by x equals t to the power of 4, subtract 32t plus 12. For part A, we're asked to find the velocity of P when t equals 3. So the velocity, that is equal to dx by dt. So we're going to differentiate our displacement function in terms of t, and then we're going to substitute in t equals 3. So differentiating this function here, we've got 4t cubed subtract 32. Now we want to find out the velocity when t equals 3. So when t equals 3, v equals 3 cubed subtract 32, which is equal to 76. So again, writing that statement to put our answer in context, the velocity of P when t equals 3 is 76 meters per second in the direction of x increasing. The reason why we're in the direction of x increasing is because we've got a positive answer. If we'd had a negative answer, we'd know that the particle would be moving to the negative direction, so when x would be decreasing. For part B, we're asked to find the value of t for which P is instantaneously at rest. So we want to find out the value of t when the velocity is 0. So we've got v equals 4t cubed subtract 32. We're going to set that equal to 0. So we get that 4t cubed is equal to 32. T cubed is equal to 32 divided by 4, which is equal to 8. So t is equal to the cube root of 8, which is 2. Now, because the question has asked us to find the value of t, which we have done, we don't then need to write down that statement to put it in context. If it had asked for the time, we would then have to write that statement. For part C, we're asked to find the acceleration of p when t equals 1.5. So acceleration, that's equal to dv by dt. So we're going to differentiate our function of the velocity. So we've got 12t squared. So when t equals 1.5, a is equal to 12 lots of 1.5 squared, which is equal to 27. Now we're asked to find the acceleration, not the value of a, so we need to write down our statement. The acceleration of p when t equals 1.5 is 27 meters per second squared.